Welcome to MyProjectBazaar.com. Let we discuss about the process image super resolution based on structured modulated sparse representation. Let me see the abstract of the process image super resolution based on structure modulated sparse representation. Enhancement of images will be more helpful in surveillances and remote sensing applications. While increasing the size of the image, the original image quality will be affected. In order to avoid the loss of quality while enhancing the image, non-local means optimized sparse method is used in this paper. The noises and the pixel differences occurring in the upsampling and downsampling of the images were identified and they were removed using our proposed methodology. The performances of the processes were measured using the performance parameters like PSNR and SSI. The input low resolution images were initially enhanced based on ridge regression. Upsampling and downsampling is employed to the enhanced image. The noises occurring due to the upsampling and downsampling of the enhanced image were handled based on the optimization using the solution for the regression problem. The noises in the optimized images were then removed using non-local means filter. Sparse coding is applied to the image and then convex minimization problem is then handled and finally reconstructed high resolution images is obtained. The performance of the process is measured based on the performance metrics and it is proved to be the performance metrics were increased comparing to the existing methods for super resolution of images. Let us see the flow of the process. The input low resolution images were taken. The low resolution images denotes the images with very small sizes. So the input low resolution images then isotropic Gaussian kernel is added to the input low resolution images. So this helps in producing blurs in the input images, which will be helpful in preserving the original pixel informations of the images. After that, upsampling and downsampling process is applied to the images, which is used to increase the sizes of the images. After that, the regression problem solvation is employed. Here the regression problem solvation indicates the identification of the noisy pixel in the images. So for the identification of the noisy pixel in the images, convex optimization problem is solved. So we got the noisy pixels locations. After that, using NLM optimization, that is using NLM filter, the identified noises were removed, and after that sparse coding coefficients were obtained. This sparse coding coefficients were helpful in the removal of the zero elements, that is unwanted elements in the input images. After that, the images were reconstructed into high resolution images, which is increased in size and enhanced in contrast. Finally, from the reconstructed high resolution image and from the input low resolution image, the performances were measured in terms of PSNR SSIM values. Let us see the running procedure of the process. If you want to run the code, select the file main.no.guy, which is present in the source code folder. Right click it and click on run file. You will get the process getting started. So first select any one of the images which is present in the dataset, or you can use any one of the images from your own. So we select any one of the images from the dataset, and first the input image is this is the input images that we have selected, and after that the isotropic Gaussian kernel is applied to the input image. As a result of this is the resulting image that we have got, and after that this is the upsampled image. this upsampled image is first enhanced in row-wise fashion, and after that it will be enhanced in the column-wise fashion, resulting in this image. So here, as a result, the input images is increased in size, but yet it has to be enhanced in a more clearer way. So this is the image with the applied Gaussian kernel. This is the next process, that is the downsampling process. And the first stage is similar to this. The input high resolution is reduced in size to this size, and after that in the second iteration it will be of the size like input image. So this is the downsampled image. It will be similar to the input image. After that, this is the image obtained after the regression problem identification. This denotes the identified unwanted pixel locations in the input images. They were removed and using NLM filter in the next step. So this is the obtained NLM filter result with the combined coefficient vectors calculated. So here we compare the histogram of the input image with the identified probability density function. So as we can see, the histogram ranges between 0 and 255, that is the maximum and minimum and the maximum pixel intensities commonly occurring in the images, and the PDF ranges from 0 to 300 for this input images. And this is the generated sparse matrix for the input image. Then after the solvation of the convex minimization problem, we obtain this enhanced image, which is more clearer than the normal upsampled images. And then finally, this is the reconstructed high resolution images. Comparing to input image, this image is increased in size, and also there is no reduction in the quality of the input image. Finally, this is the performances measured for this image. So as we can see, the PSNR value ranges lies 28, and SSM value lies between 0.8, and we know that SSM value has to be lie between 1 and -1. So if it is -1 means the two images were completely different, and it is 1 means then the two images were the same, so it lies between 0.8. So hence the both images were more similar. And after that, comparing PSNR, the value is near it is 28. So this is an enhanced image. This is an enhanced image. Thus we have increased the size of the input image into double the time of its original size. At the same time, the quality of the input images is also preserved.